Hello, my name is Dadrian Smith, and today we'll be discussing our solar system's angular momentum. What is angular momentum, you ask? I'm glad you did. Angular momentum is the measure of an object's rotational motion around its axis and its revolution around, in our case, the sun. Rotation is how a planet spins on its axis counterclockwise, unlike Venus, who does it clockwise. That's why his rotation is negative, but we'll get to that in a minute. While revolution is its spin around the sun, how it orbits around the sun. So revolution equals to orbitation. An example of rotation would be how you spin a top on its axis and it stays upright. That's how we stay upright, which is a very big deal in Earth's angular momentum. And revolution, orbit, is another big part of Earth's angular momentum. It's like a good example of that would be if you ever played Beyblade or watch Beyblade, how the Beyblade spins around the arena. This is basically a very good example of revolution. But to get into our astronomical bodies, we're going to start with Mercury, which rotates at 58.6 days on its axis and revolves at 87.97 days around the sun. So a full rotation for Mercury takes 87.97 days. So that's for a full year around the sun. And then 58.6 days on this axis. A full day on Mercury is 58.6 days with an approximate angular momentum of 0.03. Now, the reason that some of these so far are decimal points instead of scientific notations because when I put it in ChatGPT, which is the first AI resource I used for my presentation, it gave me decimal points instead of scientific notation. But for Earth, when I did it in Google Gemini, which was another AI resources I used to help me, I only use two, ChatGPT and Google Gemini. I have those at the end of the presentation. I'm not sure whether you wanted scientific notation or decimal points. I'm not sure if it mattered, so I just put both for Earth since that's our main topic. Venus, like I said, goes clockwise at a negative 243 days rotation on its axis and 224.7 days revolve around the sun. Then we have Earth with 24-hour rotation on its axis and 365 revolution around the sun with an approximate 2.7 times 10 to the power of 40 angular momentum. Then you have Mars very close to us with a 24-hour and 37-minute rotation on its axis, very similar to us, but it has a 686.98 day revolution around the sun. Now, a pattern you'll see later on in the presentation is that the further away from the sun it is, the longer revolution it has around the sun, which makes sense. But surprisingly, the further away it is, the faster its rotation on its axis is, which I find very interesting. For example, Jupiter, 9 hours and 50-minute rotation on its axis, but unlike everybody else who took days to revolve around the sun, this one takes 11 and 86 years to get around the sun with an angular momentum of 724.6. Then you have the sun. We're going to skip past all the other planets that don't really matter in the presentation. We have the sun that the rotation is axis of 35 days. It doesn't revolve around anything because it's the sun, but it has an angular momentum of 1.1 times 10 to the power of 42. We're going to skip past all the other dwarf planets except Pluto, which has a rotation of 6.387 days on its axis and 284 years around the sun, with an angular momentum of 4.2 times 10 to the power of 37. Again, the scientific notations were done in Google Gemini, and then the decimal points were done in ChatGPT. And then we're also going to talk about the moon's rotation. and revolution, which is the same for both at 27.3 days and an approximate 2.9 times 10 to the power of 34 for its angular momentum. Now, if you remember Earth's angular momentum and the moon's, if you compare the two, they're very similar and close in numbers. That can be very important later on in the presentation. But for right now, I also wanted to discuss that so our solar system has many different bodies, asteroids, comets, space dust, dwarf planets, moons, other planets, and the star, etc. But I only identified the ones that have a similar system of rotation and revolution that the Earth does for reference, because the rotation and revolution are Earth days and years. And it's just a lot easier to calculate those bodies than asteroids and comets and space dust. It's a lot less complicated. Um, if I can find my mouse. Now we're going to get into our equations. For the rotation formula and the revolution formula is basically the same thing. You have T1 divided by T2 to the power of 2 equals S1 divided by S2 to the power of 3 or to the power of 2 times 2 divided by 3. It really depends on what the question is asking for. You have a more broken down version at the top that has T or W equals 2 pi divided by or over T or W. It really depends on what the question is asking you to find or what the question's numbers have already given you. But this is just a more in-depth version of Kepler's third law. And for reference, we have Kepler's first law here, which is every planet is at an ellipse with the sun. That's basically all the planets are orbiting around the sun at an round but not circle-like rotation. If you look at it from up top, it's more like a several ovals that some are closer to the sun on one side, but it's kind of like lopsided circles. And then you have Kepler's second law, which is each planet moves at an imaginary line drawn from the sun. So basically, all the planets are rotating around the sun at the same time. They're just moving at different speeds. Sometimes they can form a straight line every few hundred thousand years, but it's not here, there, near, or there. We also have the equation for angular momentum's formula, which is L, the angular momentum, obviously, equals R times P. R being the position vector, which is where the planet is at that moment, and then which is R, the position vector, and P, which is the linear momentum, which is the speed it's revolving around the sun and the speed it's moving on its axis. P can also be broken down to mass times velocity, velocity being its speed, and mass being its, obviously weight of the planet. The units for those are usually kilograms times meters a second, and for R, it's just meters. But it's usually gonna be meters a second, sometimes squared, depending on if it has gravity or not. But what does all this angular momentum talk have to do with an Earth's conservation of angular momentum? Basically, without angular momentum, the Earth would just fall. It would just fall, either become a big giant ice rock or just implode due to the pressure of space and gravity itself. The reason we spin is for multiple reasons. One, Earth's the no. Reason number one would be the sun's angular momentum pulling all the planets towards it, making all the planets in the solar system spin around it, rotating on their axis and rotating around itself. And another key factor to Earth's angular momentum will be the moon. The way the moon rotates around its own axis on itself and revolves around the Earth itself, keeping us spinning while adding more spin to our rotation. But sadly, it's also increasing the orbital radius of the moon, which is basically just pushing the moon away from us. So eventually we won't have a moon anymore. But that won't happen for hundreds and hundreds of years. So what does all this have to do with Earth's conservation of angular momentum? Basically, angular momentum is very important because without it, we wouldn't be spinning at all. And without spinning, we just wouldn't be alive. Um, to go more in depth, though, on this part, we have this angular momentum formula right here, which is L, the angular momentum, I, the moment of inertia, and W, the angular velocity, which is the rotation rate, as I've stated before. It's basically how the Earth keeps up its spinning rotations with the help of the moon and the sun, heavily the moon, and obviously the sun. And we are at the end of our presentation. I use ChatGPT and Google Gemini as my AI documents. And yeah, that's about it. Thank you for your time.